All right, welcome back by popular demand. I'm going to keep going on AI engineering, building applications with foundation models by Chip Huyen, very near halfway through the book. All right, so term-based retrieval. Given a query, the most straightforward way to find relevant documents is with keywords. Some people call this lexical retrieval. For example, given the query AI engineering, the model will retrieve all the documents that contain AI engineering. However, this approach has two problems. Um, Oh, and I gotta turn the page, so to do that, I'll use the on-screen keyboard. So the first problem of the approach, so the first problem of keyword search, also known as lexical retrieval, is many documents might contain the given term, and your model might not have sufficient context space to include all of them as context. A heuristic is to include the documents that contain the term the greatest number of times. The assumption is that the more a term appears in a document, the more relevant this document is to this term. The number of times a term appears in a document is called term frequency, TF. All right, I'm not sure how that's a problem. So the second problem of uh, lexical retrieval, um, which is uh, the most straightforward way to find relevant documents, which is known as using keywords to find relevant documents. So the second problem associated with that is a prompt can be long and contain many terms. Some are more important than others. For example, the prompt "easy to follow recipes for Vietnamese food to cook at home" contains 9 terms. Easy to follow recipes for Vietnamese food to cook at home. You want to focus on more informative terms like Vietnamese and recipes, not for and at. You need a way to identify important terms. An intuition is that, um, and I want to try to get the okay. So an intuition is that the more documents contain a term, the less information this term is. For and at are likely to appear in most documents, hence they are less informative. So a term's importance is inversely proportional to the number of documents it appears in. This metric is called inverse document frequency, IDF. To compute IDF for a term, count all the documents that contain this term, then divide the total number of documents by this count. If there are 10 documents and 5 of them contain a given term, then the IDF of this term is 10 divided by 5, which equals 2. The higher a term's IDF, inverse document frequency, the more important it is. Oh, I see. So let's say so let's say you have 10 documents, uh, and across each of these 10 documents, there are words that are common to each. Those words are less important because they show up in every document. They're not unique to one document for the other. So, for example, let's say you have a document about cooking something, and then you have a document about being a lawyer. So you could imagine across these two documents the words the, at, that, these sort of common words are probably fairly evenly going to be dispersed between these two documents. But words like canola oil will be in the cooking document, and words like habeas corpus will be in uh, the law document. So um, it makes sense to focus less on those words that are frequent across each document and focus more on the words that are only found in certain documents but not in others. Okay, so the higher a term's IDF, the more important the term is. TF-IDF is an algorithm that combines these two metrics, term frequency, TF, and inverse document frequency, IDF. Mathematically, the TF-IDF score of document D for the query Q is computed as follows. Let T1 through TQ be the terms in the query Q. Given the term T, the term frequency of this term in the document D is f d comma or t comma d in paren. Let n be the total number of documents and ct be the number of documents that contain t. The IDF value of the term t can be written as IDF t in paren equals log of n divided by the function c given t. I think is how you would say that. Uh, Naively, the TF-IDF score of a document D with respect to Q is defined as score D comma Q equals the summation of Q up till I equaling 1, the index equaling 1, IDF of T subscript I times F T comma D wrapped in paren. And let's get a breakdown of that from the AI. Um, let's just have it unpack this unpack this equation into plain English. Let's see what that does. I hate that glitch. Whenever you pull up the on-screen keyboard, it uh, activates the prior window. Unpack this equation into plain English. Unpack this equation into plain English. All right. Well, that wasn't very useful. All right, moving on. Two common term-based retrieval solutions are static search and BM25. Static search, oh, sorry, elastic search. Yeah, I've heard of elastic search for search. So two common term-based retrieval solutions are elastic search and BM25. Elastic search developed in 2010. So really not that. Yeah, 20. Wow. Okay. Built on top of Lucene, uses a data structure called an inverted. index. It's a dictionary that maps from terms to documents that contain them. This dictionary allows for fast retrieval of documents given a term. The index might also store additional information, such as the term frequency and the document count, how many documents contain this term, which are helpful for computing TF-IDF scores. Table 6-1 illustrates an inverted index. Table 6-1, a simplified example of an inverted index. So this is a table with rows and columns. The columns are term, document count, and document index slash term frequency for all documents containing the term. So let's see what the rows are. All right, so the first row in the table is banana. The and then the yeah, so these are the words we're looking for. So we've got the word banana, and that document count. So there's 2 documents that have the word banana, 4 documents that have the word machine, and 3 documents that have the word learning. So document index, comma, term frequency for all the documents containing that term. So yeah, so we can see we've got 2 sets of parentheses for banana because there was 2 instances of that. So we've got the document index and the term frequency. So the first number is which document did it appear in. It appeared in document number 10. Um, in that document, how many times did it appear? It appeared 3 times. Now it appeared in 2 different documents. So that was the first document. What's the second one it appeared in? It was document number 5. How many times did it appear in that document? Twice. So on and so forth for all the other rows in the table. So OK API BM25, the 25th generation of the best matching algorithm, was developed by Robertson et al. In the 1980s. Its scorer is a modification of TF-IDF. Compared to native TF-IDF, BM25 normalizes term frequency scores by document length. Longer documents are more likely to contain a given term and have higher term frequency values. BM25 and its variances, BM25 plus, BM25F, are still widely used in the industry and serve as formidable baselines to compare against modern, more sophisticated retrieval algorithms, such as embedding-based retrieval, discussed next. One process I glossed over is tokenization, the process of breaking a query into individual terms. The simplest method is to split the query into words, treating each word as a separate item. However, this can lead to multi-word terms being broken into individual words, losing their original meaning. Ah, yeah, perfect. So, for example, hot dog would be split into hot and dog. When this happens, neither retains the meaning of the original term. So you don't. So when you split it, you lose whether you're talking about the definite sandwich, hot dog, or a dog that is hot. One way to mitigate this issue is to treat the most common n-grams as terms. If the bigram hot dog is common, it'll be treated as a term. Occasionally, you might want to convert all characters to lowercase, remove punctuation, and eliminate stop words like the, and, is, etc. Term-based retrieval solutions often handle these automatically. Classical NLP packages, such as NLTK, Natural Language Toolkit, SPACI, and Stanford's Core NLP, also offer tokenization functionalities. Chapter 4 discusses measuring the lexical similarity between 2 texts based on their n-gram overlap. Can we retrieve documents based on the extent of their n-gram overlap with the query? Yes, we can. This approach works best when the query and the documents are of similar lengths. If the documents are much longer than the query, the likelihood of them containing the query's n-grams increases, leading to many documents having similarly high overlap scores. This makes it difficult to distinguish truly relevant documents from less relevant ones. Embedding-based retrieval. This is all kind of going over my head. Term-based retrieval computes relevance at a lexical level rather than a semantic level. Let me just get a so we're talking about reg and agents. Okay. So we're talking about reg and agents. So we're talking about different forms of retrieval, which of course matters a lot because retrieval augmented generation requires on actually retrieving the things you're using to augment the generation. So you have to use uh, so having that done in the best way possible matters a lot. As mentioned in Chapter 3, the appearance of a text doesn't necessarily capture its meaning. This can result in returning documents irrelevant to your intent. For example, querying transformer architecture might return documents about the electric device or the movie Transformers. On the other hand, embedding-based retrievers aim to rank documents based on how closely their meanings align with the query. This approach is also known as semantic retrieval. With embedding-based retrieval, indexing has an extra function, converting the original data chunks into embeddings. The database where the generated embedded or embeddings are stored is called a vector database. Uh, Querying then consists of two steps, as shown in figure 6-3. So 6-3, a high-level view of how an embedding-based or semantic retriever works. So, okay. Number one, embedding model. Convert the query into an embedding using the same embedded model used during indexing. Number two, retriever. Fetch k data chunks whose embeddings are closest to the query embedding as determined by the retriever. The number of data chunks to fetch k depends on the use case, the generative model, and the query. So we've got the query here, sends it out, you can go to a generative model or an embedding model. Embedding model has number one, so I guess it goes here first. This is part of an index with a splitter, so external memory, documents tables, chat history, etc. can go into the index and the splitter. Then the embedding model goes out to the vector DB, external data embeddings. It also goes to query embedding. It skips the vector DB. We go right to the retriever, which is number two. And the retriever returns context relevant to query to the generative model. And now the generative model can provide a response that includes external data embeddings and external memory. All right, so the embedding-based retrieval workflow shown here is simplified. Real-world semantic retrieval systems might contain other components, such as a re-ranker to re-rank all retrieved candidates, and caches to reduce latency. With embedding-based retrieval, we again encounter embeddings, which are discussed in Chapter 3. As a reminder, an embedding is typically a vector that aims to preserve the important properties of the original data. An embedding-based retriever doesn't work if the embedding model is bad. Embedding-based retrieval also introduces a new component, vector databases. A vector database stores vectors. However, storing is the easy part of a vector database. The hard part is vector search. Given a query embedding, a vector database is responsible for finding vectors in the database close to the query and returning them. Vectors have to be indexed and stored in a way that makes vector search fast and efficient. Like many other mechanisms that generative AI applications depend on. Vector search isn't unique to generative AI. Vector search is common in any application that uses embeddings, search, recommendation, data organization, information retrieval, clustering, fraud detection, and more. Vector search is typically framed as a nearest neighbor search problem. For example, given a query, find the k nearest vectors, the native solution is k dash nearest neighbors, k dash nn, which works as follows. And I'm getting sick of using the on-screen keyboard, so let me deactivate my controller. I'm in VR here. Alright, so briefly deactivate my controller, and that should enable me to use the keyboard and mouse much more fluidly. Might need to wait for... Um, well, never mind. Yeah, keyboard and mouse still isn't working so well. Alright, it wasn't that bad, just to use the on-screen keyboard. Okay, so the native solution is k dash nearest neighbors, which works as follows. Number one, compute the similarity scores between the query embedding and all vectors in the database using metrics such as cosine similarity. Number two, rank all vectors by their similarity scores. Number three, return k vectors with the highest similarity scores. This native solution ensures that the results are precise, but it's computationally heavy and slow. It should be used only for small data sets. For large data sets, vector search is typically done using an approximate nearest neighbor (ANN) algorithm. Due to the importance of vector search, many algorithms and libraries have been developed for it. Some popular vector search libraries are FAISS, Facebook AI Similarity Search, uh, developed in 2017. Google's SCANN, Scalable Nearest Neighbors, developed in 2020. Spotify's Annoy, which is a funny name, developed in 2013. And Hinswalib, Hierarchical Navigable Small World, developed in 2016. So that's the oldest of all of these. Oh no, 2013 is the oldest. The scalable Google's scalable nearest neighbors was developed 2020, pretty recently. Most application developers won't implement vector search themselves, so I'll give only a quick overview of different approaches. This overview might be helpful as you evaluate solutions. In general, vector databases organize vectors into buckets, trees, or graphs. Vector search algorithms differ based on the heuristics they use to increase the likelihood that similar vectors are close to each other. Vectors can also be quantized, reduced precision, or made sparse. The idea is that quantized and sparse vectors are less computationally intensive to work with. For those wanting to learn more about vector search, Zilla's has an excellent series on it. Here are some significant vector search algorithms. So next there, so let's take a look at the what this series is. Oh, it's what the site is. So this is Zilla's. So this, oh, okay. So yeah, this is pretty good. It's a free tutorial. All right, let me advance the bookmark just in case. Sometimes I lose my place, so it's nice to have the bookmark there. All right, and I can keep going for quite a while. It's 5:19. So the first significant vector search algorithm mentioned in this book is LSH, locally sensitive hashing, This is an old school one developed in 1999. This is a powerful and versatile algorithm that works with more than just vectors. This involves hashing similar vectors into the same buckets to speed up similarity search, trading some accuracy for efficiency. It's implemented in FAISS and Annoy. The next vector search algorithm is HNSW, Hierarchical Navigable Small World, developed in 2016. HNSW constructs a multi-layer graph where nodes represent vectors and edges connect similar vectors, allowing nearest neighbor searches by traversing graph edges. Its implementation by the authors is open source, but it's also implemented in FAISS and Milvus. The next vector search algorithm is product quantization, developed in 2011. This works by reducing each vector into a much simpler lower dimensional representation by decomposing each vector into multiple subvectors. The distances are then computed using the lower dimensional representations, which are much faster to work with. Product quantization is a key component of FAISS and is supported by almost all popular vector search libraries. The next vector search algorithm is IVF, Inverted File Index, developed another fairly old school one, developed in 2003. IVF uses k-means clustering to organize similar vectors into the same cluster. Depending on the number of vectors in the database, it's typical to set the, oh, and my page turn failed. It's typical to set the number of clusters so that on average there are 100 to 10,000 vectors in each cluster. During querying, IVF finds the cluster centroids closest to the query embedding, and the vectors in these clusters become candidate neighbors. Together with product quantization, IVF forms the backbone of FAISS. The next algorithm is Annoy, approximate nearest neighbors. Oh yeah, funny name, developed in 2013. Annoy is a tree-based approach. It builds multiple binary trees where each tree splits the vectors into clusters using random criteria, such as randomly drawing a line and splitting the vectors into two branches using this line. During a search, it traverses these trees to gather candidate neighbors. Spotify has open sourced its implementation. There are other algorithms such as Microsoft's SPTAG, Space Partition Tree and Graph, and FLAN, Fast Library for Approximate Nearest Neighbors. Even though vector databases emerged as their own category with the rise of RAG, any database that can store vectors can be called a vector database. Many traditional databases have extended or will extend to support vector storage and vector search. Comparing retrieval algorithms. Due to the long history of retrieval, its many mature solutions make both term-based and embedding-based retrieval relatively easy to start. Each approach has its pros and cons. Term-based retrieval is generally much faster than embedded-based retrieval during both indexing and query. Term extraction is faster than embedding generation, and mapping from a term to the documents that contain it can be less computationally expensive than a nearest neighbor search. Term-based retrieval also works well out of the box. Solutions like Elasticsearch and BM25 have successfully powered many search and retrieval applications. However, its simplicity also means that it has fewer components that you can tweak to improve its performance. Embedding-based retrieval, on the other hand, can be significantly improved over time to outperform term-based retrieval. You can fine-tune the embedding model and the retriever either separately together or in conjunction with the generative model. However, converting data into embeddings can obscure keywords, such as specific error codes. For example, error code 99, which is spelled EADDRNOTAVAIL. So it's like um, Eadrot, dronot, Eadronot avail, not avail. Yeah, yeah, I see, I see. So I think not avail. Because remember, this is a error code, so not avail, not available. So it's something. Um, so it's like not available. So EADDR not available would be the area code. Or product names, making them harder to search later on. This limitation can be addressed by combining embedding-based retrieval with term-based retrieval, as discussed later in this chapter. The quality of a retriever can be evaluated based on the uh, quality of the data it retrieves. Two metrics often used by RAG evaluation frameworks are context precision and context recall, or precision and recall for short. Context precision is also called context relevance. Context precision. Out of all the documents retrieved, what percentage is relevant to the query? Context recall. Out of all the documents that are relevant to the query, what percentage is retrieved? To compute these metrics, you curate an evaluation set with a list of test queries and a set of documents. For each test query, you annotate each test document to be relevant or not relevant. The annotation can be done either by humans or AI judges. You then compute the precision and recall score of the retriever on this evaluation set. In production, some RAG frameworks only support context precision, not context recall, to compute uh, context recall for, oh, missing a period there. To compute context recall for a given query, you need to annotate the relevance of all documents in your database to that query. Context precision is simpler to compute. You only need to compare the retrieved documents to the query, which can be done by an AI judge. If you care about the ranking of the retrieved documents, for example, more relevant documents should be ranked first. You can use metrics such as, oh, well, so if you care about it, so if you want more relevant documents to be ranked first, you can use metrics such as NDCG, normalized discounted cumulative gain, MAP, mean average precision, and MRR, mean reciprocal rank. For semantic retrieval, you need to also evaluate the quality of your embeddings. As discussed in Chapter 3, embeddings can be evaluated independently. They are considered good if more similar documents have closer embeddings. Embeddings can also be evaluated by how well they work for specific tasks. The MTEB benchmark, uh, Munigoff et al. 2023, evaluates embeddings for a broad range of tasks, including retrievals, classification, and clustering. The quality of a retriever should also be evaluated in the context of the whole RAG system. Ultimately, a retriever is good if it helps the system generate high quality answers. Evaluating outputs of generative models is discussed in chapters 3 and 4. Whether the performance promise of a semantic retrieval system is worth pursuing depends on how much you prioritize cost, and latency, particularly during the querying phase. Since much of RAG latency comes from output generation, especially for long outputs, the added latency by querying, embedding generation, and vector search might be minimal compared to the total RAG latency. Even so, the added latency can still impact user experience. Another concern is cost. Generating embeddings costs money. This is especially an issue if your data changes frequently and requires frequent embeddings generation. Imagine having to generate embeddings for 100 million documents every day. Depending on what vector databases you use, vector storage and vector search queries can be expensive too. It's not uncommon to see a company's vector database spending be one-fifth or even one-half of their spending on model APIs. Table 6-2 shows a side-by-side comparison of term-based retrieval and embedding-based retrieval. Table 6-2, term-based retrieval and semantic retrieval by speed, performance, and cost. So this table has two columns. First column is term-based retrieval. Second column is embedding-based retrieval. The first row is for querying speed. Much faster, so term-based retrieval is much faster than embedding-based retrieval. For embedding-based retrieval, query embedding generation and vector search can be slow. All right, so the next factor to consider whether or not to go with term-based retrieval or embedding-based retrieval is performance. For term-based retrieval, typically strong performance out of the box, but hard to improve. Can retrieve wrong documents due to term ambiguity. And for embedding-based retrieval, can outperform term-based retrieval with fine-tuning. Allows for the use of more natural queries as it focuses on semantics instead of terms. Cost. So then the final factor to consider is cost. For term-based retrieval, it's much cheaper than embedding-based retrieval, and embedding vector storage and vector search solutions can be expensive. With retrieval systems, you can make certain trade-offs between indexing and querying. The more detailed the index is, the more accurate the retrieval process will be, but the indexing process will be slower and more memory consuming. Imagine building an index of potential customers, adding more details, for example, name, company, uh, email, phone, interests, makes it easier to find relevant people, but takes longer to build and requires more storage. In general, a detailed index like HNSW provides high accuracy and fast query times, but requires significant time and memory to build. In contrast, a simpler index like LHS is quicker and less memory intensive to create, but it results in slower, less accurate queries. The ANN Benchmarks website compares different ANN algorithms on multiple datasets using four main metrics, taking into account the trade-offs between indexing and querying. These include the following. Recall, the fraction of the nearest neighbors found by the algorithm. Query per second, QPS, the number of queries the algorithm can handle per second. This is crucial for high traffic applications. Build time, the time required to build the index. This metric is especially important if you need to frequently update your index. For example, because your data changes. Index size, the size of the index created by the algorithm, which is crucial for assessing its scalability and storage requirements. Additionally, Bayer, BEIR, benchmarking IR, um, in 2021 is an evaluation harness for retrieval. It supports retrieval systems across 11 common retrieval benchmarks. To summarize, the quality of a RAG system should be evaluated both component by component and end to end To do this, you should do the following things. Number one, evaluate the retrieval quality. Number two, evaluate the final reg outputs. Number three, evaluate the embeddings for embedding-based retrieval. All right, so the next section is combining the two. You don't have to just go with one or the other. You can combine them. Let me advance the bookmark. Let me take a look at the clock. Well, let me take a look at how much is left. If we have a major section coming up soon, that'll be a good. I'm looking at a stopping point. I kind of had enough, and I'm in VR, so there's a thing on my face that's starting to get kind of uncomfortable. All right, so let's take a look at the clock. 40 minutes. You know what? I think I'm good with that. Yeah, I need to get out of VR. So that's it. Thanks for watching. See you in the next one.